On the screen, we can see the electrical diagram and the refrigeration circuit of an automotive air conditioning system. Next, we will study step by step how this system works and analyze both its electrical behavior and its thermodynamic behavior. At this moment, the system is turned off. For this reason, the pressures on both gauges, low and high, are balanced and remain static. When the system is off, there is no pressure difference between the high side and the low side because the compressor is not running. In this state, the refrigerant is at rest and is distributed throughout the circuit in equilibrium with the ambient temperature. For a system that uses a 134A refrigerant and with an ambient temperature above 35 degrees Celsius, approximately 95 degrees Fahrenheit, the static pressures are approximately 90 pounds per square inch. On the other hand, if the system operates with our 1234YF refrigerant, the pressure on both gauges will be approximately 100 pounds per square inch. These resting pressures may vary slightly depending on the altitude above sea level and the influence of the heat generated by the vehicle's combustion engine. When the driver starts the vehicle engine, whether gasoline or diesel, and then switches on the air conditioning from the internal console, the system activation process begins. In this case, this console, powered electrically by the vehicle battery, includes components such as the evaporator, the blower, temperature control, airspeed control, and the expansion valve. From this console, an electrical activation control signal is sent. This signal first passes through a device called a pressure switch. The pressure switch is a safety switch that monitors the system pressures. If the pressures are within safe operating values, the pressure switch allows the flow of electrical current. This current is then directed to the compressor clutch. The electromagnetic clutch engages or disengages the compressor shaft with a pulley driven by the engine belt. When the clutch is activated, the compressor begins to rotate and refrigerant circulation starts. Simultaneously, the pressure switch also sends current to a relay. This relay has two control pins, numbered 85 and 86, and two load pins, numbered 30 and 87. The control pins activate an internal coil that, when energized, generates a magnetic field. This magnetic field closes an internal switch in the relay, thus allowing current to pass to the first fan. This fan is located at the front of the vehicle, right in front of the condenser coil. Its main function is to dissipate the heat from the hot refrigerant coming out of the compressor, helping it to condense. When the clutch is engaged, the compressor starts operating. It receives movement directly from the vehicle engine through the accessory belt. Once running, the compressor begins to suction low-pressure refrigerant gas and compresses it, sending it to the condenser as hot high-pressure gas. At that moment, the system now has two differentiated pressures, a high pressure on the compressor discharge side and a low pressure on the suction side. For example, in a system using our 134A refrigerant, the low side gauge pressure, with the engine at idle, should be around 36 pounds per square inch. On the high pressure gauge, it should be around 150 pounds per square inch. On the other hand, if the system operates with our 1234YF refrigerant, the low side pressure will be approximately 39 pounds per square inch, while the high side will reach around 170 pounds per square inch. These pressures may vary depending on the combustion engine speed, outside temperature, and the efficiency of the condenser and external fan. If the operating conditions are normal, the system will maintain stable balance and properly cool the vehicle cabin. However, if the outside temperature is very high, or if there is a greater internal thermal load due to a higher number of occupants, the system will need to work harder. If in addition to this, the driver accelerates the engine, the pressure on the high side can rise significantly. If this pressure reaches, for example, 200 pounds per square inch, the pressure switch detects this critical condition and activates an internal switch. This new switch sends an additional electrical signal, this time intended to turn on a second fan in the condenser area. The purpose of this second fan is to increase the airflow through the condenser coil to reduce the refrigerant temperature and thereby lower the high side pressure. This second fan is also controlled by a second relay. Again, pins 85 and 86 receive the control signal, activating the internal coil. This allows pins 30 and 87 to supply the current needed to operate the additional fan. Thanks to this automatic intervention, the system avoids damage caused by overpressure, ensuring safe and efficient operation. This type of protection is vital for the durability of the compressor and the entire automotive refrigeration system.